one more Telecom seminar. Welcome everybody. This is an event which is hosted by Technology Innovation Institute in Abu Dhabi. We usually organize the seminars in a bi-weekly basis. So for today, I'm pleased to welcome Professor Uigao. Professor Uigao is a chair professor at School of Computer Science and the director of Intelligent Network and Computing Research Center at China, and also a visiting professor at the University of Surrey, UK. He received a PhD degree from the Queen Mary University of London, UK in 2007. He has then worked as a lecturer, senior lecturer, reader, and chair professor at Queen Mary University of London and University of Surrey, respectively. His research interests include smart antennas, sparse signal processing, and cognitive networks for mobile satellite systems. He has published over 200 peer-reviewed journals and conference papers, and over 7,000 citations. He was a co-recipient of the European Horizon Prize Award on Collaborative Spectrum Sharing in 2016, and he was elected as Engineering and Physical Science Research Council Fellow in 2017. He's a member of the Board of Governors and distinguished lecturer of IEEE Vehicle Technology Society. He is the chair of IEEE Wireless Communication Technical Committee. He was the past chair of IEEE Technical Committee on Cognitive Networks. He has been an editor of several IEEE transaction journals, symposium chair, track chairs, and other roles in organizing committee of several IEEE consort, VTS, and other conferences. So the title of his talk today is Compressed Spectrum Sensing and Learning from Theory to Practice. And basically, the presentation will discuss various aspects of compressed spectrum sensing to address existing challenges and enhance the practical implementation. And he also presents a software-defined system for cooperative spectrum sensing on millimeter wave with active real-time spectrum sensing. So, Professor Uigao, thank you once again for accepting our invitation. It's a great pleasure for us to have you as the speaker of the seminar. And without further ado, the floor is yours.
Okay, thank you, Daniel, for the introduction. It's my great pleasure to presenting some recent work we have made by my past PhD students and myself. And Daniel is a very good friend, and been a long while we haven't meet or see each other. Through this opportunity, I'm really glad. And I also thank you for TII, Technology Innovation Institute, invitation. So today I'm going to share the compressed spectrum sensing and learning from theory to practice. And the talk will include mainly 4 parts and plus a little bit conclusions. I would like to discuss some fundamentals of the compressed spectrum sensing. It's a topic has been researched for a while, and we have some new understanding and produce some challenge through the process. Then second part, I will discuss some spectrum reconstruction and support detection algorithms with the traditional recovering algorithms. And the third part, we will discuss a bit compressed spectrum sensing practical systems we developed through the years. And hopefully we will produce some open challenges, open source software and hardware to the community, and then we can produce more research output and take more research challenge ahead of us. And finally, I also discuss a bit learning from the sub-Nyquist samples, which we as a team, as myself, we organized 2 challenges in the past, and then summarize a little bit. So as the motivation, we probably know this quite well. And if you are researching or doing research in the field of cognitive radio, cognitive network, spectrum sharing, probably you see this diagram quite often. We are currently allocating the spectrum from a few kilohertz to 300 gigahertz, as shown in the diagram on the slide. So this is the allocation mainly with a fixed policy. We can see the spectrum nearly fully filled with various activities, from TV to radio to mobile to Wi-Fi, and a lot of other spectrum, such as the millimeter wave or terahertz, becoming more and more interesting. However, in the booming of data race and data science and video, as well as gaming, we have a lot of data or digitized contents. We're transferring from the physical world to the cyber world. Therefore, the amount of binary bits to be shifted from the physical world into the cyber world becoming massively increased. So the spectrum we have can carry those bits, becoming a challenge or become more and more scarce. And we have 400% resources in need in comparison to the spectrum we have today. So how we can efficiently use the spectrum? Of course, there are traditional ways by using MIMO or different coding techniques and to making the spectrum becoming more efficient. But on the other hand, we can see that the spectrum mostly has been used with a fixed allocation policy. So there are times, idle times for the spectrum to be utilized by other users rather than the pre-allocated users. So this leads to the concept of dynamic spectrum access or cognitive radio. And since 1999, and by Mitra and produced the concept, and we have following this cognitive cycle for a long while. We are trying to produce in the research community, try to produce from spectrum sensing, spectrum analysis, then making spectrum decision, and then we're making the access, and then making a cycle of that. So there are various practical systems were produced, such as the TV white space by both the Ofcom in the UK and FCC in the US. However, such a dynamic system still based on the narrowband sensing, and also some combined with the database concept. So for the cognitive radio to be used in practical scenario is still very challenging. And so far, we did not see a lot of very wideband applications of such a cognitive radio devices. So one of the major challenges is the spectrum is so wide. So in our group, so we're focusing on the wideband spectrum sensing and detection techniques. So the aim is to reduce the ADC, the analog to digital converter ability, because those ADCs generally are expensive. And for example, for a 2 gigahertz bandwidth or sampling per second ADCs is worth over $1,000 US, or even more expensive in a few years before. So how we can overcome such a Nyquist sampling request and to achieve a using by lower speed ADCs and to achieving a more efficient sampling efficiencies. So from the spectrum, we can see most of the spectrum are sparse. They are only using a particular frequency band allocated on a few bands. So one of the first group to produce the sub-Nyquist sampling concepts for the spectrum detection. So we firstly making the spectrum sparse representation. Select the diagram below to show. Then second part is in the middle of the diagram to produce the reconstruction algorithm. And then we can detect the frequency of frequency spectrum and its occupancy. And furthermore, of course, we can do more than that based on the subsamples as our GBSense challenge produced. We can do the modulation detection or the modulation recognition. And also in our group, we're starting doing the demodulation work. So in this presentation, we're mainly focusing on this periodic non-uniform sampling architecture. That is the multi-coset sampler. Of course, there are other groups such as the Caltech group making the AIC, analog information converter architecture, or the Israel group by Professor Oda and making the MWC modulated wideband converter architecture. Our group were focusing on the multi-coset sampler. So as the diagram on the left shows that one of the advantage of the multi-coset sampler is that we can using the uniform narrowband ADC, but adding a variable delays to achieve the random sequence effect, so that we can put in a randomness into a unified signal, and so that the randomness such as the tau1, tau2 to tau-p, and to making the sensing matrix. And then as the diagram on the right indicated, we have the coefficient matrix X, which the original signal with the white blocks are unoccupied, the colored green, blue, or yellow blocks are occupied. So that through the sensing matrix, the random delay convolute with the coefficient matrix X, we can produce the sample or subsampled matrix Y. So if we can making such a sparse representation of the spectrum with the hardware architecture, then we can utilize the more efficient algorithm such as the convex approximation algorithms methods, or sparse Bayesian learning algorithms, or greedy pursuit algorithms to recover the subsamples, so that the overall architecture becoming simple for the hardware, and then using the computing power and with the powerful algorithm together, and to achieve the sub-Nyquist sampling with the recognition of the signal itself. So that's our primary purpose to carry on this research. So the second step after the sparse representation is to recovering the signal. So the recovering algorithms or the reconstruction or the support detection, if we don't recover the full signal or itself, then we need to recover the spectrum support. So with this information, we can identify the spectrum whether it is occupied or not. So based on the 1960s Lando's rate, the lambda f have to be have enough number of the support. So that's the theoretical limit for perfect reconstruction. So the practical minimum average sampling rate normally is 4 times of that, or over 200% or twice of the theoretical bound. Otherwise, we are not able to fully recover the signal, have some parts missed. So what caused the gap between the theory and the practice? So this is one of our recent work by Dr. Zhiheng Song. He recently graduated, to answer. 2 of us have working on this very hardly, and to understand whether it's from the noise interference or the computational efficiency or what else. So based on our understanding of the theory and the hardware design, we are thinking about the sampling pattern, which is the randomness of the delay architecture with the tau. So this is a subset of the multi-coset sampling. Whether this subset is optimal, whether this subset is meeting the restricts asymmetry property, the RIP property, and the mutual incoherence property, MIP. So based on our guessing, we start to try to understand how we can choose such a subset to make the multi-coset sampling becoming more efficient to be recovered in the later stage. So therefore, we try to optimize this through the mutual coherence of the such a distance between the elements. So the unlinear discrete optimization problem were formed, and we try to providing solution space size between the L and P. So with this in mind, we started building this algorithm and running simulations. So the sampling pattern design through these deterministic or heuristic algorithms, and try to evaluate our ideas. So the general sampling pattern use a sensing matrix with a strict MIP threshold, and satisfy the RIP of the order K equals to Q over log LP, and whether that can be applied to a wide range of partial Fourier matrix applications. So that's in the deterministic method. For the heuristic measures of optimization is through the iterative approach. So we try to building up simulations to understand the sampling pattern, whether it is the uniform selection or the GMSPG. Our proposed pattern will be better based on different sparsity levels. So as the diagram indicating here, we can see for the different approach for the field, finite field-based deterministic generations, we have the performance on the diagram on the left, or the mutual coherence random selection, or the mutual coherence sequential forward selection. So the performance of some proposed pattern design method can see that is progressively getting better towards the last diagram. We are having a slightly better performance for the higher sparsity levels. So we're also looking at the MMV model, the multiple block. So this is the block MMV model to reduce the unnecessary reconstruction, to reduce the complexity and the speed of the algorithm. So by reshaping the MMA according to block factor B, as shown in the diagram here, and we try to take out the actual reconstruction out of our algorithm, so that we're saving the computing power and increasing the speed of the reconstruction. So the complexity has been reduced, and the sensing matrix still can keep its isometry property. By using the MMA block MMA model to reduce the unnecessary reconstruction, we are trying to testing the idea as well. So we're producing the wideband signal as shown on the diagram on the left by reshaping the MMA according to the factor B as indicating in the previous slides as well. And also we're testing when B in different values, and from 2 to 4 as the diagram indicating on the right. We can see when the B goes to 4 with the circled symbol curves can achieving slightly better detection probability property. And with of course with more process P, we are having better performance. Once we have more than 8 cosets, and we are achieving close to 99% detection rate. So for the support recovery from the noise signal by using double threshold matching pursuit principle is also improving the performance of the algorithm. So we are mainly dealing with the real world signal with noise embedded into the signal. We produce the hardware and also through our testing spectrum analyzer and spectrum monitoring system to collecting the real world signal and to produce the algorithm, try to be able to tackle those problems. So the performance of the greedy pursuit algorithm we have produced for a while in our early papers, such as the MPO SOMP, SOMP. And we do find such a double threshold matching pursuit can improve the performance slightly, and also with different parameters and in comparison with the SOMP. As the diagram on the right shows more clearly, we are improving the false alarm probability much better. And for the diagram on the left, we can see that for the detection probability, they are more or less the same. For a optimized cooperative or compressive spectrum sensing scheme, we try to integrate the block MMA model and the sampling pattern design and the DTMP algorithm together, and to produce the final algorithm and to showing the performance we can achieved. So we are using the same hardware without any change of the hardware, and with only linear increase of the time of the complexity, we are achieving nearly over % performance improvement by reducing the average sampling rate for the perfect spectrum reconstruction. So this giving us a lot of advantage, especially when we implement the algorithm in our hardware. So we are approaching to the theoretical limit, theoretical minimum rate from 200% into 120%. This is a big jump in terms of the theoretical design from the theory into the practice. But of course, lately we are also probably in the TII has making some research as well, or participate in our challenge. The AI is probably by using the artificial intelligence, machine learning, different learning algorithms or transformer, and we could improve the performance better. So this is an open challenge. We are hoping interested researchers can producing more gain, and eventually, if we could break the theoretical bound in some ways. So after our theoretical design, we are starting making the first step for the hardware implementation, which is the software-defined radio system. We're trying building such a system with the support from National Instruments, and to implement the algorithm we developed in this system to verify the algorithm. So this system is based on the NI millimeter wave transceiver system. However, we modify the system by using the TX and RX, the TX as a transmitter, the RX as a detector. And by, as we can see that of the diagram on the right is the real-time implementation. The diagram on the left is the modules we used to build up such a system. We have massive support from National Instruments and their team giving us a lot of help. We implement the 3GPP FR2 millimeter version of this. And this millimeter version of the 3GPP FR2 is based on the 8 100 gigahertz channels, and each channel have 100 megahertz. Sorry, it's 8 100 megahertz channels. Each channel have 100 megahertz with 8 channels. So it's 800 megahertz in total. So once we build up the system, we build up the software. So we are building such a chain software to showing that real-time sub-Nyquist wideband spectrum sensing, especially for the millimeter wave. This is a 2 gigahertz band with the frequency domain showing here, the time domain showing on the top. That's what the transmitter transmitted out as the previous diagram shows. So we have 100 megahertz channels. We have 2 channels, 3 channels, and then this is a more filtered, clean version of the bands of the signal. And then the following 2 red diagrams with the curves, with the signals, they are the at the receiver side. We try to we implement our sub-Nyquist sampling algorithm to showing the 2 channel and 3 channel captured by the SOMP and the other recovering algorithm. We can see the speed is nearly close to real time, but of course it's not completely real time, but is in the millisecond level. We can catch the signal and try to recover the signal. So our hardware system we're building up is based on the 850 megahertz ADCs. And we try to verify this algorithm whether we can achieve a 2 gigahertz band with signal to capture 2 or 3 100 channels each. So with the software-defined radio system were recognized, then we are starting building the hardware of such a system. So this is the real implementation of the hardware. So we have the power splitter, mainly to getting the RF signal in to split into 8 ways. But of course, we are using the IQ streams. So we have 16 streams here. And then these 16 streams fitting into 850 megasample per second ADCs. So these ADC were controlled by the clock, distributed clocks. And then our comprehensive sensing algorithm implemented in these lattice FPGAs. So the data for our challenge, for example, is output from here or from a Raspberry Pi connected our SPI output with the snapshots. So here listed most parameters for our design of the system. So our capability of this hardware can detecting 2 gigahertz bandwidth signals with 850 megasample per second ADCs, and equivalently is 400 megasample per second. And of course, the output is LVDS interface with 32 parallels, and the speed is up to 300 megahertz, and with the 14 bits ADC in resolution. So this hardware we developed. Furthermore, we replaced the early system we developed with a millimeter wave, which is the digital part. So we replaced their existing 2 gigahertz sampling boards with our own boards with the IQ data. Again, we are making a output of such data and to creating a real-time implementation through the millimeter system. And we also produce a number of systems. So that's the overall comprehensive spectrum sensing from theory to practice. Then after such a work we produced, we also building up learning algorithms from the subsamples. And I believe TII have produced really, really good work. And by Yutian and probably with Daniel's team and a number of famous researchers together, they are winning the first prize of our GP-Sense challenge, learning from the sub-Nyquist samples. Of course, we produce our benchmark algorithms. Here are showing some basic ideas how we are learning the algorithms from the problem formulation and then making the basic assumption and then distribute the coefficients. Then we're producing the algorithms overall here through different recurring algorithms from the SOMP, from the sparse Bayesian learning algorithms. We can see that the learning through performance increasing with the number of the cosets increased. But of course, we're not only interested in learning, but also producing other techniques, such as the anomaly detection, whether we have the anomaly behavior of the spectrum from the subsamples. So we are creating the autoencoder for the spectrum reconstruction and using the extracted features for anomaly detection. And such a performance that's increasing the ability to detecting the anomaly subsamples. Recently, we're also working on the modulation recognition as the probably TII's team working on it from the subsamples, but also like demodulation a number of ways, and is still in a great challenge. And we also we are also going to announce the third challenge in the coming summer, and to produce the newer challenge, especially the learning from the subsamples. So to conclude my talk today, is about how we are building the theory, comprehensive spectrum sensing theory, into a practice platform. And especially from the technical point of view today, we are trying to trying to approaching the theoretical bound and close the gap between the theory and the practice. And we are reducing the requirement of the samples from 200% into 120%. And also we implement the hardware and from the software-defined radio to verify the algorithm into the circuits development to developing the hardware. And then finally, we're showing two examples. Of course, there are a lot more examples, is the learning from the sub-Nyquist samples. And basic spectrum reconstruction problem, modulation recognition, anomaly detection, demodulation, or a number of ways to be continued. We're hoping if you are interested, please do get in touch with us. We're also providing the hardware for our closed collaborators and to tackle the research challenge in this field. And thank you for your listening. And I would like to advertise a little bit. I'm the chair of the HOV ComSoc WTC. The meeting is coming very soon for today. If you are interested, please joining in. And thank you for listening. And if you have any questions, please do let me know. And I'm very happy to answer and discuss with you. Thank you, Daniel.
Thank you. Thank you, for this very informative talk. Now we'll move for the questions and answer section. So if you have any question, please write in the chat box. Yeah, we have one question from Tian. He's a researcher in TII. Actually, he won the prize that you mentioned.
Yes, well done. Yeah, many congratulations.
Yeah, so the question is, in the P-way parallel sampling, can P be as large as possible in theory? And what issues we cause in practice with a very large P is used?
So that's a very good question, actually. The P is the subset. Of course, the bigger the number of the subsets you choose, the better performance. This respect of other parameters. So of course, that's very key point. But when we're choosing the P, before we're choosing the P, actually, we are trying to developing the subbands. So in the frequency domain, we're talking about subbands, but in time domain, of course, the resolution of the time step. So how many time subbands you are choosing are also affecting the number of P you are choosing. So that's I would treating this as the resolution. I could say that's very accurately, but it can be treated as the resolution of for the multi-coset sampling for the P.
Okay, thank you.
Yeah. I hope I answered your question. Is the way you are asking.
Okay, I have a general question, actually related to spectrum sensing. Usually, when you are sending data, you cannot perform sensing, right? Spectrum sensing. And the sensing period, it can, I mean, it determines the degree of the degradation of primary user performance. So it's desirable usually to spend as little time as possible for spectrum sensing to improve data transmission. And also increase the spectral monitor frequency to prevent the primary user from being affected. So there is usually a conflict between the data transmission rate and the spectrum sensing time resolution. So how we can manage this trade-off?
Yes, this is a very good question. Actually, this is of course, firstly is the limitation of the compressive sensing techniques. is only applied to the sparse signal. But also in another way, in my group, I guess a lot of other research group also trying to building up or try to break the theoretical limit, and whether such a subsamples and can apply or compressive sensing techniques can apply to less sparse signal or even not sparse signal. But of course, there is a hardware sampling limits. But I think for the development of the AI or the advancement of the AI techniques, maybe we able to finding ways and transfer the signal in a way that we could more close to the Lando's rate and more or even break the Lando's rate limitation. I hope, but I must say we definitely will be able to close from our, we have some studies we're hoping to produce or to be published in later. And then can showing some of the indication, but is always the limitation. You have the primary user more and more, and then of course you have less spectrum, sparse spectrum.
Yeah, definitely. I think a mechanism is required to limit the secondary user transmission activity and power based on the primary receiving user detection sensitivity, right?
Yeah,
so this is crucial.
Absolutely. So that that will be goes to like between multiple levels, different transmission power. So by coding different waveforms, that can making parallel transmissions.
Okay. And questions from the attendees? Yes, another question that I have is regarding the sparsity. Actually, the sparsity of spectral utilization is crucial for the implementation of compressed sensing methods, right? But with many users share a broadband spectrum with the primary users, this assumption may not hold. So how to distinguish primary users from many secondary users?
So that's exactly the question I discussed a little bit early. So if the spectrum is not sparse, then these techniques wouldn't work. I have to admit that from the theory itself. But whether the AI technique or with our a little bit experience with the such a machine learning algorithms, we can see the possibility has been giving us that we could work in more and more crowded spectrum and could identify the subsamples. So for this research we are doing is mainly try to using the algorithm to reduce the hardware complexity and the cost. So as I mentioned earlier, if we are 2 gigahertz or 2 gigasample per second ADC is cost over $1,000 US. From we use 50 megahertz ADC, like a cost $100, less than that, probably a few bunch of cheap ADCs. So that is the research we're trying to work on. But of course, the scenario, question, I completely understand. For such a crowded case, this technique wouldn't work. We have to talking about more higher level ability by using the sequential scanning. So this is a part of thinking in our mind. We are also can try to do. Actually, for the wideband, of course, is one way is that we're using a wideband ADC or our approach, several parallel ADC to get the signal instantly. But another way is, or in our communication system, we're swiping the spectrum by using a narrowband. We for example, using like 20 megahertz or like 100 megahertz maximum, is swiping the spectrum and to get the signal in, and then we're detecting the signal whether used or not. this is a traditional way to doing it. And even for the spectrum analyzer they are using such a technique. It's still able to doing a lot of work in most of the scenarios. Of course, you say that, I have a multi-bands and suddenly come out and you don't know where they are, then our technique would be better. And then you have the scenario that you have all the wideband, all the sub channels are all occupied. Then none of these will work.
Yeah.
We have to go to the most expensive approach to get the wideband ADCs.
Yeah, it's a topic worth to be studied. To active a high probability reconstruction without increasing the complexity, right? The hardware complexity.
Yes.
This is
exactly. So basically, we're computing based on our hardware, we can building this sequential scanning and the wideband without crowded or with a sparse signal. That's what we can do. For example, our traditional system, they have to use a bandpass filter to filter all the other signal out. So it's only single band. For our hardware or our ability, we can have multi-bands together at the same time, but distributed into a 2 gigahertz wide bandwidth. We get all the signal out at the same time. This is the advantage of this system. Yeah.
Yes. We are moving to the end of the seminar. Actually, Professor Wigao has another commitment in some minutes. So I would like to thank him once again for the time and for this excellent presentation. And also I'd like to thank all the attendees. And as I mentioned at the beginning, this presentation has been recorded and will be available at the TII YouTube channel. So please feel free to disseminate through the colleagues and groups. So thank you once again, Professor Wigao.
Okay, thank you, Daniel. I'll see you in a bit, I think. Thank you. Bye for now. Thank you for joining my research talk. Thank you. Bye-bye.
Thank you. Bye.